Alright, so here's a quick recap of what we've got so far. We studied first order with respect to one component, first order overall. Rate equals k times a to the first power. The exponential version of that integrated rate law is a at time t equals initial A concentration times e to the minus kt. And the half-life is equal to 0.693 over k. Remember, the important thing is that is a constant. The other version that we studied was second order with respect to one component and second order overall. Rate equals k times a squared. This is the second simplest case, and the integrated rate law was quite different, and it is 1 over a, the concentration of a at time t equals kt plus 1 over the concentration of a0. And the other important result here in this case is the half-lives were not constant. They depend on the initial concentration in the denominator, so as the initial concentration lowers, the half-lives get longer. So this constant versus increasing half-lives is another way to distinguish between a first order and a second order reaction. Now, so people that do this for a living, I am not one of them anymore, can actually look at a curve of the concentration as a function of time, like this one, and know if it's first order or second, because the curves have a slightly different shape, especially when the rate constants get very large. So the concentration drops faster when it's first order versus second order reactions. And also, again, as the rate constant for both of them increases, the concentration is going to drop quite a bit too. All right, so we talked about the two orders, and these are the only two we're going to talk about in this class. So how do you tell? So here is a reaction where we've got, this is called perfluoroethylene, C2F4, and they can combine to form this C4F8 square looking thing. And you might want to know if this is a first or second order process. And so let's recall what the integrated rate laws looked like. And we're able to reduce or express both first and second order integrated rate laws in the form of a linear equation. And in case of a first order process, the natural log of the concentration versus time is expected to be a straight line. And if it's a second order process, a plot of 1 over the concentration of, in this case, the C2F4 versus time will be linear. So remember, it's always, y versus x. So let's look at some graphs. So typically what you do in this case is you run the experiment, you measure the concentration as a function of time, and you plot the data for both suspected orders, in this case first and second order. And this is the result. So I want you to look at these and remember what we said these plots would look like for the two, and tell me if this is a linear, this is a first order or second order process. So hit pause, think about it, and we'll come back. Now clearly this data is much more of a straight line than say this one is. And if you doubt that, well, just draw a straight line. Of course, now I have to try to draw a straight line as best I can. Versus here, try to see. Yeah, so that's not a straight line. Or the other one is much more of a straight line. In real life, it's usually not this clean, but you still hope that one equation is a better fit than other. And then look at which one is actually the better fit. And in this case, it is this one. And this was the plot of the inverse concentration as a function of time, implying that this is a second order process, and that the slope of this line will be equal to positive k. and that one is not linear.